Morning. Okay, already almost the syllabus is over, so we'll discuss some important topics. So in second unit we'll discuss about the fast Fourier transform. So already uh, initially we discussed about the DFT discrete Fourier transform. It can be used to perform linear filtering. Okay, so here DFT is used to perform only linear filtering. But what is meant by linear filtering? Set of algorithms known as FFT. So DFT is used for linear filtering. So set of algorithms known as fast Fourier transform, which is proposed by Cooley and Hackey in 1963. So FFT is highly efficient procedure for computing the DFT of finite series and requires less number of computations than that of direct evaluation of DFT. So it is efficient. It consisting of highly efficient procedure for computing the DFT of a finite series and requires less number of computations, right? So it is highly efficient. It is having highly efficient procedure and it requires less number of computations than that of direct evaluation of DFT, right? Okay, so FFT is based on decomposition and combining them to get the total transform. First of all, we have to decompose the uh, transformation and combine. Finally, we'll combine. Okay, so why this FFT is needed? Why this fast Fourier transform is needed? So the direct evaluation of DFT using x of k is equal sigma n equal 0 to n minus 1 x of n into e power minus j 2 pi n k by n requires n square complex multiplications and n into n minus 1 complex additions, right? N square complex multiplications and n into n minus 1 complex additions. Thus, for large values of n, it is not possible. So, it is for direct evaluation. So, it requires n square complex multiplications and n into n minus 1 complex additions, right? So for this one, large values of n, this is not possible. So that's why by using the FFT algorithms, the number of computations will be reduced. It is highly efficient. It is having highly efficient procedure for computing the DFT of finite series and requires less number of computations than that of the direct evaluation of DFT, right? Okay, now coming to the direct evaluation of DFT. So if you take the formula DFT formula, that is x of k is equal to sigma n equal to 0 to n minus 1 x of n into e power minus j 2 pi n k by n. Here k is in between 0 and n minus 1, right? 0 and n minus 1. So that is a discrete Fourier transform. Discrete Fourier transform. Discrete Fourier transform. So DFT is equal to x of k is equal to sigma n equal to 0 to n minus 1 x of n into e power minus j 2 pi n k by n. 0 is less than or equal to k is less than or equal to n minus 1. That will be considered as equation number 1. Now substituting omega n equal to e power minus j 2 pi by n. So replace e power minus j 2 pi by n by omega n. So it will become omega n power n k. So x of k equal to sigma n equal to 0 to n minus 1 x of n into omega n power n k, where the k is in between 0 to n minus 1. That is equation number 2. So we can write this as a sigma n equal to 0 to n minus 1 real part of x of n plus imaginary part of x of n. Okay. So real part of x of n plus j into imaginary part of x of n into real part of wn power n k plus j into imaginary part of wn power n k. So let it be considered as equation number 3. So that is equal to sigma n is 0 to n minus 1 real part of x of n into multiply these two. So real part of x of n into real part of wn power n k plus sigma n equal to 0 to n minus 1 j into imaginary part of x of n into real part of wn power k plus sigma n equal to 0 to n minus 1 j into real part of x of n. Okay, plus like that we will multiply these two components. So it will become sigma n equal to 0 to n minus 1 real part of x of n into real part of wn power n k minus sigma n equal to 0 to n minus 1 imaginary part of x of n into imaginary part of x of n, no, omega n power n k plus j into sigma n equal to 0 to n minus 1 im into x of n imaginary part of x of n into real part of wn power n k plus sigma n equal to 0 to n minus 1 real part of x of n into imaginary part of wn power nk, right? So where w omega n or wn is nothing but a fiddle factor is called fiddle factor. So first of all, we'll take the expression for DFT, that is x of k equals sigma n equals 0 to n minus 1 x of n into e power minus j 2 pi n k by n. Okay. Now replace e power minus j 2 pi by n as wn. So it will become x of n into wn power nk, right? So now we will divide this as a real part and imaginary parts, right? So real part and imaginary parts, okay, so that it will become real part of x of n plus j into imaginary part of x of n. Similarly, real part of wn of nk plus j into imaginary part of wn power n. Multiply these two so that we get the expression like this. So where omega n or wn is called fiddle factor. So equation 3, we can evaluate one value of x of k. So the number of complex multiplications required is n. So to evaluate all n values of x of k, the number of complex multiplications required is n square. So to evaluate all n values of x of k, the number of complex multiplication required is n square. Okay. So to evaluate one value of x of k, the number of complex additions required is n minus 1. To evaluate all n values of x of k, the number of complex additions required is n into n minus 1, right? So direct evaluation of DFT is basically inefficient because it does not use the symmetry and periodicity properties of the fiddle factor omega n or wn. So direct evaluation of DFT is inefficient because it does not use the symmetry and periodicity properties of the fiddle factor wn. So uh, these two properties are symmetry property and periodicity property. So symmetry property is wn power k plus n by 2 is equal to minus wn power k, and periodicity property is wn power k plus n is equal to wn power k, wn power k. So it exploits FFT. So coming to this is about the DFT. Coming to the FFT, it exploits two basic properties of fiddle factor and reduces the number of complex multiplications required to perform DFT from n square to n by 2 log n to the base 2 n square. So here the complex number of complex multiplications required in DFT is n square. But here it is n by 2 log n to the base 2. Okay, n by 2 log n to the base 2. Okay, so it is FFT is exploits the two basic properties, that is symmetry property and periodicity property of fiddle factor wn, and reduces the number of complex multiplications required to perform DFT. Okay, from n square to n by 2 log n to the base again to the base 2. So for example, 64 point sequence, if we take the 64 point sequence in DFT, n square is 64 square, that is 4096. In FFT, that is n by 2 log n to the base 2, that is 64 by 2 log 64 to the base 2, that is 192. So here the number of computations will be reduced. Okay. So here in FFT, we have two classes of FFT algorithms are there. Those are decimation in time, and second one is decimation in frequency. Decimation in frequency FFT, decimation in time FFT. Okay. So first of all, we will take the decimation in time FFT, DIT FFT, DIT FFT. So this is also known as the radix to DIT FFT, the radix to DIT FFT. The number of output points m can be expressed as n equal to 2 power m minus integer. Okay, so the number of output points n can be expressed as n equal to 2 power m minus n minus integer. Let x of n is the endpoint sequence. Here n is the azimuth power of 2. Okay. So decimate or break this sequence into two sequences of length n by 2, where one sequence consisting of even indexed values of x of n and other of odd indexed values of x of n. Okay, even so here the sequence will be uh, divided as even indexed values of x of n and odd indexed values of x of n. So that is xc of n is equal to 2n, where n equal to 0, 1 up to n by 2 minus 1, and so O of n is equal to 2n plus 1, where n is varying from 0 to n by 2 minus 1. That is equation number 1. N point dft of x of n can be written as x of k is equal to sigma n equal to 0 to n minus 1 x of n into e power minus j 2 pi n k by n, right? 2 pi n k by n. Okay. So sigma n equal to 0 to n minus 1 x of n into e power minus j 2 pi by n is nothing but wn. So it is wn power n k, where e power minus j 2 pi by n equal to wn. Here k is varying from 0 to n minus 1. Okay, that is equation number 2. Okay, now separating x of n into even and odd indexed values of x of n, we obtain x of k equal to sigma n is 0 to n minus 1 x of n into wn power n k plus sigma n equal to 0 to n minus 1 x of n into wn power n k. So here n is 2n. This is the even indexed value, and this is odd indexed value. Say xi of n equal to 2n and xo of n equal to 2n plus 1. Replace n by 2n here, so that it will become sigma n equal to 0 to n by 2 minus 1 x of 2n into wn power 2n k plus sigma n equal to 0 to n by 2 minus 1 x of 2n plus 1 into wn power 2n plus 1 into k, right? So it is equal to sigma n equal to 0 to n by 2 minus 1 into x of 2n into wn power 2n k plus sigma n equal to 0 to n by 2 minus 1 into x of 2n plus 1 into wn power 2n k into wn power k. So or extract this to the outside, so it will become wn power k into sigma n equal to 0 to n by 2 minus 1 into x of 2n plus 1 into wn power 2n k. That is equation number 3. Or we can write this as xc of n into wn power 2n k plus wn power k into sigma n equal to 0 to n by 2 minus 1 into xo of n into wn power 2n k. That is equation number 4. Right, we can write wn power 2 is nothing but e power minus j 2 pi by n whole power 2, or it is nothing but e power minus j 2 pi by n by 2, or we can write this as w n by 2. So wn power n power 2 is equal to w n by 2. That is equation number 5. So replace w n power 2 as w n by 2, so that it will become sigma n equal to 0 to n by 2 minus 1 xc of n into w n by 2 power n k plus w n power k sigma n equal to 0 to n by 2 minus 1 into xo of n into w n by 2 power n k. So that is equation number 6. This is nothing but n by 2 point dft of even indexed sequence, and this is n by 2 point dft of odd indexed sequence. We can write this as x of k is equal to xc of k plus wn power k into xo of k. That is equation number 7. Okay. So where k ranges from 0 to n minus 1. For n by 2 sequence, k ranges from 0 to n by 2 minus 1. For k is greater than or equal to n by 2. So wn power k plus n by 2 is equal to minus wn for k. That is symmetry property, equation number 8. For now x of k for k is greater than or equal to n by 2 is given by x of k equal to xe of k minus n by 2 minus wn power k minus n by 2 into xo of k minus n by 2 for k equal to n by 2 plus 1 up to n minus 1. That is equation number 9. For direct evaluation of DFT, let us take n equal to 8. Then n is n by 2 is 8 by 2, that is 4. So when n equal to 0, then xc of n equal to 2n, xo of n equal to n plus 1. So if n is 0, then xe of n becomes xe of 0, that is 2 into 0, that is 0. Okay, so this is for even value index, even index values, and this is odd index values. So it will become xe of 0 is 0, xe of 1 is 2, xe of 2 is 4, xe of 3 is 6. Similarly, when n is 0, xe of 0 equal to 1, xe of 1 is 3, xe of 2 is 5, xo of 3 is 7. From equation 7, we have x of k is equal to xe of k plus wn for k into xo of k, for 0 is less than or equal to k is less than or equal to 3. K. Here k is varying from 0 to n minus 1. Here n is 4. N is 4. Then it is n minus 1. It is here n is 8. This is 0 to n by 2 minus 1. That is 8 by 2. That is 4 minus 1. So it is 3. That is equation number 10. From equation 9, we have x of k is equal to xe of k minus n by 2. Okay. So C of k minus n by 2 minus Wn for k minus n by 2 into xo of k minus n by 2 for n by 2, that is 8 by 2 is less than or equal to n by 2, n minus 1, 8 minus 1, that is 7. Okay, by substituting different values of k in equation number 10 and equation number 11, we get here k equal to 0 to 3, here k equal to 4 to 7. Okay, so by substituting these values, so k equal to 0 to 3, then x of k will become xe of k plus wn power k into xo of k. So it will become x of 0 is equal to xe of 0 plus w8 power 0 into xo of 0. X of 1 is xe of 1 plus w8 power 1 into xo of 1. X of 2 is xe of 2 plus w8 power 2 into xo of 2. And x of 3 is xe of 3 plus w8 for 3 into xo of 3. Similarly, here k is varying from 4 to 7. So n by 2 is 4. So x of k is xe of k minus n by 2 minus wn for k minus n by 2 into xo of k minus n by 2. Okay. So it is x of 4. Suppose 4 k is 4, then xe of 4 minus 4, that is 0, minus w8 for 0 into xo of 0. Similarly, x of 5 is xe of 1 minus w8 for 1 into xo of 1. X of 6 is xe of 2 minus w8 for 2 into xo of 2. And x of 7 is xe of 3 minus w8 for 3 into xo of 3. So from the above set of equations, we can find that x of 0 and x of 4, x of 1 and x of 5, x of 2 and x of 6, x of 3 and x of 7 have same inputs. Okay, x of O is obtained by multiplying x of O with W8 for 0 and adding the product to XE of 0, right? Similarly, x of 4 is obtained by multiplying xo of 0 with W8 for 0 and subtracting the product from XE of 0, right? So in the same manner, we'll find out the remaining values also. Okay, this operation can be represented by a butterfly diagram. This is called butterfly diagram. Okay, butterfly diagram like this. So butterfly diagram, this is xc of 0, xc of 0 plus w8 for 0 into xo of 0. So this is xc of 0, that is a, and b is xo of 0. Here it is here the output is a plus w8 for 0 into b. Here the output is a minus w8 for 0 into b. Okay. So A is XE of 0 plus W840 into XO of 0. Here A is XE of 0 minus W840 into B, that is XO of 0. This is called butterfly diagram. Okay. So now the value of X of K for K equal to 1, 2, 3, 4, 5, 6, 7 can be obtained. Construction of 8-point DFT from the 4-point DFT. 4-point DFT is like this. So it is divided into 2 and by 2. That is 4-point DFT, 4-point DFT. So it is XC of 0 equal to X of 0, XC of 1 is X of 2, XC of 2 is X of 4, XC of 3 is X of 6. Similarly, here the inputs are XO of 1 is X of 1, XO of 3 is X of 3, XO of 3 is X of 5, and XO of 4 is X of 7. So here it is, these are the outputs. XC of 0, XC of 1, XC of 2, XC of 3, XO of 0, XO of 1, XO of 2, XO of 3. So these are hidden factors. W840, W841, W842, W842. So this is X of 0, X of 1, X of 2, X of 3, X of 4, X of 5, X of 6, and X of 7. So the sequence X of n is shuffled into even indexed sequences XCFN and odd indexed sequences X naught of n. First of all, if it is 8-point DFT, it can be shuffled into two DFTs, 4-point DFTs. If it is 4-point DFT, it can be shuffled into two DFTs, 2-point DFTs. Okay. The inputs to the butterfly is separated by n by 2 samples, that is 4 samples. The n by 2 point DFTs can be expressed as combination of n by 4 point DFTs, right? So XC of K for 0 is less than or equal to K is less than or equal to n by 2 minus 1 can be written as XC of K is equal to XCE of K plus Wn for 2K into XEO of K for K equal to 0 to n by 4 minus 1, right? So n by 4 minus 1 is 2 minus 1, that is 0 to 1. Okay. Next, XC of K is equal to XCE of K minus n by 4 minus Wn for 2 into K minus n by 4, XEO of K minus n by 4 for n by 4 is less than or equal to K is less than or equal to n by 2 minus 1. So here K value is 4 minus 2, that is 2 to 3. So XE of K is n by 4 point DFT of even numbers. XEO of K is n by 4 point DFT of odd numbers. In the same way, XO of K is equal to XEO of K plus Wn for 2K into XO of K for K. For K is in 0 to n by 4 minus 1, and XO of K is equal to XE0 of K minus n by 4 minus Wn for 2 into K minus n by 4 into XOO K minus n by 4 for n by 4 is less than or equal to K is less than or equal to n by 2 minus 1, that is equation number 13, where XOE of K is n by 4 point DFT for even numbers, XOO of K is n by 4 point DFT for odd numbers, right? So for n equal to 8, we can represent this like this. For n equal to 8, XE of n is divided into even and odd indexed sequences as XE of 0 equal to XE of 0 and XEO of 0 equal to XE of 1, right? XE of 1 is XE of 2 and XE0 of 1 equal to XE of 8. Now from equation number 12 we have XE of 0 equal to like this. Okay, so so the construction of 8-point DFT from 2 4-point DFTs and 4-point DFTs from 2 2-point DFTs like this. Okay. So this is the flow graph of decimal time algorithm. 4 points, 2 points. Destination and time sequence at each state. So this algorithm has been called destination and time sequence at each state. The input sequence is divided into smaller sequences. So the input sequences are decimated at each state. From the program, several important observations we have is here. First point we have to know is bit reversal. So input samples of index 0 to 7 are there. So we will represent this 0 to 7 in binary representation like this. Then we'll take bit reversal binary bit reversal of this one. So that will get 0, 4, 2, 6, 1, 5, 3, 7. So first up is we have to take the bit reversal of the inputs 0, 6, 2, 7, 0, 0, 4, 2, 6, and 1, 5, 3, 7. Of number of multiplication for the direct evaluation of DFT versus FFT algorithm are like this. So number of stages are m divided by m 2, 3, 4, 5, 6, 7, 8, 9, 10. So the number of points that is denoted by n. So n equal to 2 power m. So 2 power 2 that is 4, 2 power 3 that is 8, 2 power 4. Number of complex multiplications you direct evaluation and FFT algorithm. Here we use direct evaluation it is n square by FFT algorithm it is n by 2 log n to the base 2. So it is like this, and the speed improvement factor is n square by n by 2 log n to the base 2. N square by n by 2 log n by 2 n by 2 log n to the base 2. So summary of steps of radix to DFT FFT DIT FFT algorithm. Okay, radix to DIT FFT decimation in time FFT algorithm. Okay, first step is number of input samples n equal to 4m, where m is integer. The input sequence is shuffled to bit reversal. So the number of stages in the flow graph is given by m equal to log n to the base 2. Each stage consists of n by 2 butterflies. Inputs and outputs for each butterfly are separated by 2 power m minus 1 samples, where m stage index, that is first stage m equal to 1, and for second stage m equal to 2, and so on. The number of complex multiplications is given by n by 2 log n to the base 2. The number of complex additions is given by n log n to the base 2. The Tittle factor components are a function of stage index m and is given by k equal to nt by 2 power m, where t equal to 0, 1 to up to 2 power m minus 1. The number of sets or sections of butterflies in each stage is given by the formula 2 power m minus m. The component exponent repeat factor ERF, okay, which is the number of times the exponent sequence associated with the m is repeat, is given by 2 power m minus m. Okay, that is about the summary of decimation in time FFT algorithm. Okay, just concluding the today's class. So from the next class we will see the remaining one. Okay, these are very important questions. Okay, this I am concluding the today's class. Thank you.